All right, so um, let's take a look at this magnitude weight pruning with keras. Yeah, this is interesting. Overview. Welcome to the tutorial for weight pruning, part of Tensorflow. What is weight pruning? Weight pruning means literally that eliminating unnecessary values. Okay, yeah, sure. Great. So remove near zero or low weight values. Why is this important? Because we can make everything sparse, and then we can save space and computation. And okay, cool. Let's go through this video. Go through this tutorial on colab. Here we go. So we are in colab. Let's just take a look here. Get this all sized up. Great. Okay. Copyright, sure, let's take a look at that. License, great. Okay. Magnitude-based weight pruning. Okay, let's read this over. I think we just read this. How does it work? Two things to clarify. We just kind of zips it up. Two things worth clarifying. The technique and API are not TensorFlow Lite specific. Okay. By itself, a sparse model will not be faster to execute. Just enables the back end. Such. However, we'll take advantage of this. Okay. Okay, to recap, the tutorial will train an MNIST model with keras, great. MNIST, super easy. Train a pruned MNIST, great. Compare the size, yep. I didn't want to do that. Where did that go? Okay, compare the size, convert the prune model, great, and show. I think we're going to skip this, TensorFlow Lite. I'm really interested in this pruning. Show how the prune model works. Okay. So setup. To use the pruning API, install TensorFlow model optimization package. Okay. Since you will be training a few models in this tutorial, install the TensorFlow GPU package to speed things up. Yeah, nice. Okay. I don't want to do any of this. Might totally mess this up, but let's, how do we do this? Is that how we do it? Now let's try this code. I think it's like TensorFlow. Oh, right. Let's go up here to runtime and change runtime. Okay, yeah, Python 3 GPU, great, save. Okay, so let's just start running this. It is not authored. Yeah, run it anyways. Yep, and then setup. Good. Okay, so I think I say TensorFlow version equals 2.x. Let's see what happens. Great, unknown. Maybe like this. Great. Okay, let's add some more code. Let's say import TensorFlow as tf and import. Let's see if we can do this as TMO. I don't know. TensorFlow model optimization. What do they call it later on? TensorFlow, eager execution, zip. Oh, I think this is all going to be... All right, well, let's try it anyways. I'm trying to get used to using TensorFlow 2.0 and keras. Just trying to get out of using TensorFlow 1.4. 1.14 rather. Spend a lot of time doing that. Just, try to adopt the new things. Let's try this. Invalid syntax. I don't know, man. Just, like, forget that. Let's just do, we got user. I think eager execution is by default. Let's try that. Does that work? Yeah, great. Let's try this. Tensor board's on, great. So Tensorflow, tf.keras, Tensorflow GPU, Tensorflow model optimization. I don't know what that is. So let's just put a comment here, which is we skipped this part, and let's make that a section, and let's move this up. We ran that, and what's this? That's a double. Great. So we can just like, let's yoink these. Let's import those also. Okay, already loaded. Yeah. Okay, so we skip those, right? Yeah. Eager execution, all of that. Okay, prepare the training data. Well, let's see what they're doing here. They're saying, always reading other people's codes. Always takes some time. Images, columns. Yeah, we know that already. Training data, keras, MNIST load. Yeah, we got all of that. Backend image data format. Channels first. What are they? This is usually just so easy. What are they trying to do here? They're saying channels first. Why would they want channels first? Oh, if this, what? Let's see what this is. I don't think I've ever seen this. Channels last. Yeah, I just, huh. Yeah, well, okay, well, let's just, I have not seen that before. Let's just delete that. Interesting. Yeah, okay, so reshape. You know, we don't need this. You can just say like -1. Anyways, input shape is that. Great. Okay, so train and test, they've reshaped. So let's do something here. Let's say print x train dot shape, and let's actually print that out. Train dot shape, and let's do the same thing for test. And the rest of this, let's just add it to the next code block, and let's run this. Cool, that's what I expected. There's supposed to be 60,000 digits, about 6,000 of each number, and then 10,000 training examples. So we got the shape we wanted. What are they doing here? They're saying defining what the input shape is. Yeah, that's cool. As type float 32, great. And then they're dividing it by 255 because these values are actually from 0 to 255. Let's just show that. We can just do that here. We can say x dot train dot min, and so the minimum 0 and max is 255. So this is just normalizing it. We could also handle that with like batch normalization, but that's fine. and then we just print this out. Shape, yep. Convert class vectors to binary class. Okay. To categorical. Okay, let's see what all that does. Let's delete that. That's great. So let's just take a look at, let's shape. Oh, I don't need to put shape in like that. Great. And now let's just take a look at the first, I don't know, like 5. There we go. Yeah, so it's categorical. Cool. Done. So let's train it without pruning. Okay, so let's see what they've got here. L equals tf.keras.Layers. Okay, so they can just say L dot. Okay, nice shortcut. Not a fan. It works. Okay, so they're saying let's start with the sequential model. It's fine. Let's do convolution 2D. Let's say L dot input. No. Okay, here's the trouble with this. Let's just execute this so that we can get some code completion here. Great. L dot input layer, and then the input shape. Great. Is, well, we have that already. We have that here, input shape. Oh, let's say input shape. Great. So that should be our first layer. Let's take a look at this next one. Oops. Okay, so what they said? Okay, so filters is, I can't ever remember what order these are in. Okay, filters, kernel size. Oh, I thought that you had to put the kernel size in like this. But that's pretty cool. You can just put in a single number. Okay. So what's this layer doing here? This layer here is saying let's do a two-dimensional convolution using a 5x5 window over the whole input, and we're going to pad the outside with 0 so that after we do this convolution we'll end up with the same 28 by 28 because that's our input shape, is 28 by 28. Yep. And oh, we don't need this input here. And then we're going to turn that into 32 features. Okay. Then we do max pooling. Again, I don't really like the fact that these aren't actually named. Pool size is 2 by 2. We should be able to do the same trick up above like the kernel size. I wonder. This would be strides equals 2 by 2, padding same. Okay, so what this is going to do is it's going to go over our 28 by 28 image, which is still going to be 28 by 28 after this convolution because we say that we want to add padding so that the size is the same. It's going to go over this convolution, which is not going to be 28 by 28 by 1 anymore. It's going to be 28 by 28 by 32. So it's going to be like a big chunk of data, a large tensor. And what this is going to do is it's going to go over, do a pooling 2 by 2, so looking at every window of 2, and skipping, so that it's not like here I have a bit of a picture of some. There we go. Hey, it was 16 by 9. So it's like looking at like these 4, and then instead of looking at these 4, it's skipping and just looking at these 4, and so on. And then when it gets to the end here, it doesn't look at these 4, it skips down, right? So it skips 2 this way and skips 2 this way. And then padding, again, it makes sure that we pad it enough so that the math works out so that it's just exactly 2, a half rather. So all the pooling works. You know, if we had like a little extra half over here, it'll add pooling, but we don't because it's 28 by 28. Okay, we do a batch normalization. So if we did this batch normalization, if we did one like right here off the input, then so if we did that, which we're not going to, then we wouldn't need to divide equal by 255 because it would be normalized already. But we just did this, and so cleaned it up. This would do, just a note here, if we did this batch normalization off of the input layer, it would be like white balancing the whole image. And that means that like certain parts of the image that, you know, are either overused or underused will get like renormalized, and some parts of the image that are highly underused but used once in a while, then the batch normalization will make that parts like a really high spike when it's used infrequently. So you have this Gaussian distribution of use. So it might not actually be what we want to have happen on the input layer. Okay, let's delete that. So then we batch normalize. That means that now, so at this point, what we're going to have is not 28 by 28 by 1, because, well, we had those 32 from here, and then we had the size reduced in half because of the pooling. So this is going to be 14 by 14. And the values in here are going to be an average of 0 and a standard deviation of 1 because they are normalized. So all of these 32 features in this 14 by 14 image, these 32 layers, not features rather, kernels, no, filters, they call them filters, yeah. These 32 filters, the value is going to average 0 and have a standard deviation of 1. So sometimes they could be up to 2 or 3 or down to -1. Anyways, that's where they're going to be. And that's a way of making sure that our values here don't get like way out of control, like super high or super low. So this layer here, it's going to get this input, which is really nice, not regularized, but normalized by batch. I can get into that in another video. Okay, so what's this convolution going to do? Well, again, let's just call these what they are, filters. Kernel size equals 5. So and instead of 32 filters, we're not going to go up to 64. We're going to have a 5 by 5 window again, padding, and the activation of ReLU, regularized linear unit. So that equation is simply ReLU is the function of x equals x if x is greater than 0. Now let's do it like this. Equals, yeah, if x is greater than 0, else 0. There, that's what ReLU is in a nutshell. That's all that is. Ooh, really fancy. So that's what this convolution is going to do. And we're going to do another max pool. So this guy here, instead of 14 by 14, is going to be 7 by 7 by 64. And we'll see that in the summary. That'll be nice. Then we flatten that. So I don't want to flatten that just yet. That's a lot. That's 7 by 7. Like there's a whole bunch of these parameters that are highly, whatever. I'll just use the example as is. So flatten it. Well, after I flatten it, I'm going to have 7 times 7 times 64. Let's do the math. 7 times 7 times 64. I should have 3,136 features. Okay, let's just copy that. So this should be like that. I'm just putting this before I do the model summary just to make sure that I understand this model. And then I have this dense layer of 1,000 items. So I'm going to take this and multiply by this. So like how many free parameters is that going to get? That is a lot of free parameters. Did I do that right? 3136 times 1024. Are you kidding me? That's a crazy number of free parameters, right? So if we want to talk about that in terms of, let's put this free parameters, go away. Free parameters in terms of, our training set is 60,000. What's going on? Why is that complaining? 60,000 items, and then each one has 784 elements in it. So let's calculate that. So 60 times 7 times, let's just 28 times 28 because I can't remember what that is. So 47 million. So our training data has 47 million data points. Only like 60,000 training examples. So with 3 million free parameters, we should be able to easily memorize 60,000 training examples and just totally overfit this. Oh, okay, so then they use a dropout of 4 to try to regularize that. I am not a fan of dropout, and that's like for an entire other video. I mean, it's all right, but man, does it cause a lot of covariance, and that's just, yeah. Let's play with that in another video. There's other things you can do other than dropout, so we could talk about those at another time. But whatever. Okay. So then we do a final dense layer with again units equals that. Let's do this here. With the number of classes, and we do a softmax. All right, so let's see how we did with our calculation. So yeah, that's a lot. What do we have? Oh, I was off by a few. No, whatever. And then yeah, so there's quite a number of free parameters. That's a lot of trainable parameters for something that's supposed to be so trivial as MNIST, but that's what they want to do. Oh, okay, so here, let's take a look at the shape, right? So we had our input shape, and then we see that this is 28, 28, 32. That's this first guy here, and that's what we expect, right? Because it's just adding filter layers. And then after our max pool, it got down to 14 by 14 by 32, right? So the image is a 14 by 14 image, and instead of having 1 pixel per, place on that image, it has 32 filters. And then we do a batch normalization. It doesn't change anything as far as the shape. And then we do our next convolution, and our next convolution doesn't change the shape again, and it just adds. And then we do our max pooling, and that changes the shape. And then we have quite a number of parameters, and we just do like a dense on quite a number of parameters, which is, sorry, quite a number of features, and that gives us like a crazy number of parameters. We could, if we wanted to reduce that, is to do another convolution and get that down, but I'm just going to leave it with theirs and just see what happens. So let's load this tensor board. Cool. I don't use tensor board much. Let's give it a go. Here we go. No dashboards are currently active for this data set. It's inactive. Okay. Let's run it. Okay. So what it's saying here is here's this callback for this tensor board. We're going to compile it. We're going to use just categorical cross entropy. That's this is y times log of y, let's call this ground, y underscore means ground truth, times the log of y, which is our estimate. We're going to use an atom optimizer, yeah, so I can talk about that in another video. Metrics, and we're going to report accuracy. Let's see, yeah, we're going to fit this, batch size, this is the batch size we talked about before. The how many epochs did we say? I think we said 10. Yeah, well, it's saying 10 right here. So verbose, yeah, it's talking about it. Callbacks, there's our callback up there, validation set. That's interesting. It's just using the entire test set as validation. Okay, sure. I mean, why not? It's not serious. So we'll just do that. And then at the end, we'll do a final evaluation and report our score. And we got 98%. Meh. It's all right. I mean, we're not trying to get like a super awesome model here. The point is the process of pruning these extra things and creating sparse matrices. Okay, let's just take a look at what we got here. I don't really use TensorBoard all that often, so let's see. This is our neural net, starts here with our input, convolutions, max pool, batch normalization. Batch normalization has some trainable parameters, and then convolution, max pool, flatten, dense, dropout, dense, and then our loss in our matrix. Yeah, okay, nice. Do we have, that's just our graphs. I'm sure there's like scalars, smoothing. Okay, let's refresh. I thought we could see how the training went. Where is the training? What am I? I'm missing something. surely there's more to this than just looking at this. I've seen the tensor board before. Let's see what this has to say if I just run it again. Okay, reusing. There we go, great. So there's the accuracy, and here's the loss. So the training looked like it did pretty well, and then so the training went well, the validation seemed to go well. It was better than the training as far as the loss was lower, and then the loss got worse. And here, again, the training did really well, and then the test, or rather validation, got worse. So our regularizer didn't seem to save us, and yeah, well, that's how it did. I mean, there's so much to say about this. Like, you know, having this last layer, there we go. Where's the model? Having this last layer here with just an insane number of parameters, like it could totally memorize the output, and not really in a good, like, generalizable way. So that might be what we're seeing here. Yeah, I'm so tempted to play with that because I love playing with that. But this video is about trying to make this more of a sparse encoding. Okay, so let's take a look down here. Let's just take a look at how the training went. It looked all right. Training here got up to, I mean, 98%, whatever. Okay, it's good. Let's move on. So let's save the original model for size comparison for later. Okay, cool. Backend agnostic way to save restore models. We'll make an H5. Okay. We'll save it. I've never done it this way before. Keras model save, model include optimizers, false. Okay, saved. Look at that. Cool. And we call that the Keras file. Okay, we can use that later. We provide a prune low magnitude API to train models with removed connections. The Keras-based API can be applied at the level of individual layers or the entire model. We will show you usage of both following sections. At a high level, the technique works by iteratively removing zeroing out connections between layers, given a schedule, into target sensitivity. Okay, yeah, that totally makes sense. So, you know, what the idea here is that, you know, we've got all of these fairly large matrices, these matrices here, the convolution, this convolution, and then this dense. Those are just really large matrices. This first one's not that big, only 800 parameters. This is just batch normalization. And then this convolution here, which is 51,000. So what it's saying is we're going to try to zero out some of these, the low ones, and after we zero them out, we're going to see within a threshold by removing zero connections in a given and target sparsity. Okay, so we're targeting a particular sparsity. For example, a typical configuration will get 75% sparsity by pruning connections every 100 steps, starting from 2000. You know, this reminds me of another video I watched where, his name's Professor Winston, and he talks about making a, you know, really deep fully connected dense neural net, just way over the number of parameters that you need. And he shows how it can, learn a particular model really well, and then he goes and he just like kills huge, vast amounts of the connections, and then shows that it still does really well. But then he restarts the whole experiment with only the post-pruned number of connections. So here, if we have 75 sparsity, that means that we only have 25% of the connections. So we remade that neural net with that lower number of parameters with like the 25%, and showed that I couldn't actually solve the problem. I'll see if I can find that video and put a link in the description. It's pretty neat. So what comes to my mind about this is, sometimes we want to make a model that has enough parameters for it to learn the data, but then it's kind of overfit to the data. And then if we can then cut it back, it can then be the minimalistic model to solve that problem. But if we start with a minimalistic number of parameters, we may not actually be able to learn the model. That's what this guy, Patrick Winston, showed in a pretty tight little example. Okay, so let's build a Prune model. In this example, we show how to use the API at the level of layers and build a Prune MNIST solver model. In this case, the Prune low magnitude receives as parameter the keras layer whose weight we want to be pruned. Okay. Screens pruning algorithm. Please refer to the GitHub page for documentation. Great. Okay, sparsity. Yeah, and schedule starts. Yeah, okay. Let's try to import this. See what happens. Fail. Okay, what happened? No module. That's because we didn't, way back up here, I think I skipped it. We skipped this part. Install Tensorflow model optimization. Okay, so let's try that. I don't even know if it's going to work with warning, following packages are previous image, you must restart the runtime. All right. Restart the runtime. Yes. We're going to have to retrain the model. That's fine. Okay, so we ran all of this. We ran that, and this, and this, and this. Is it going to complain second time? No. Great. Okay, I'm still going to skip all of that. I don't need that anymore. Let's run this, and this, and this, and this, and this. All right. And then after that runs, we will. So let's move on. And we should be able to do this. All right, let's take a look. Now I lose so much time just watching this. It's like a little spaceship going. I don't know, man, the amount of time I waste just watching this going is just insane. Yeah. Parts of my life I will never get back. Oh, got really different results this time. We're getting, up into the 99%. Oh. Inconsistent. So, oh, there we go. Yeah, 98. starting to overfit. Back up high again. Yeah, that's a whole thing to talk about too. Like this validation accuracy jumping up and down so much. And what to do about that. Interesting. And then we had our test accuracy of 99.28. Oh, wow, that's much better than before. We saved it to H5. We ran this. Okay, just demonstrate how to save and restore a pruned keras model. In the following example, we first train the model for 10 epochs, save it to disk, and finally restore and continue for 2 epochs. With gradual sparsity, 4 important parameters are begin sparsity, final sparsity, begin step, end step. The first 3 are straightforward. Let's calculate the end step given the number of training batches. Okay. We're going to do 12 epochs. Number of training samples is our number of training samples, sure. And our end step is number of training samples divided by our batch size, which is 128 as type int times the epochs. Okay, let's do it. Pruning parameter. Never played with this before. Pruning schedule. Polynomial decay. Let's see what I say about this. Pruning schedule of polynomial decay. Okay. Initial sparsity, 50%. Final sparsity, 90%. Begin, 2000. End step is the end step. Why does it begin step? First 3 are straightforward. Begin step. That's when you begin applying the sparsity. Frequency 100. Okay, let's look this up. This is Tensorflow model optimization sparsity. Okay, let's read this. Great. That was super not useful. Let's do this. Let's say, oh, here we go. No, that's not what I meant. I meant help. Okay, so initial sparsity, final sparsity, begin step, end step, power, frequency. Okay. Sparsity at which the pruning begins. Sparsity at which the pruning ends. Okay, step at which to begin pruning. Okay, yeah. It seems like it meant, but power. Exponent to be used in the sparsity function. All right. And only apply pruning every frequency step. Okay. So And power, this is the exponent here. Exponent, I'm assuming, is current sparsity. Okay. Interesting. Let's remove that. Pruning model. Let's just run that by itself. See what happens. Good, it ran. Pruned model. Sequential. Sparsity, prune, low magnitude. We're not using the, like, I don't see us reusing the old model. We're just like defining a whole new one, it looks like. Yeah, it's not like we're taking the old one as input. We're just defining a whole new one. I don't really like that. No. Yeah. Okay, well, we'll see what we can do with that. So there's our convolution, same as before, but it's not the same weights as before. So how would we do if we wanted to use the same weight? So we'd do something like, we'd say first conv equals like this. And then we would just put that in here. And if we did the same thing when we used this same variable and didn't redefine it, we did that up above, then they would both share the same weights. So that's what we could do. So let's just leave that for now. We have this max pooling, and then let's just call this second conv equals this guy here. We have max pool, our batch norm. There's our second convolution, our max pooling, our flatten, and then here we have this dense network. Okay, so then we're going to call this big dense, because that's how I feel about it. And then we're going to have final dense equals this guy here. So big dense, we can substitute him in. And final dense, we can substitute him in. Okay, still the same dropout, which I want to talk more about dropout, but not now, not now. Okay, let's see what happens. Okay, looks pretty much the same as before, except there's a hell of a lot more parameters. It looks like twice the parameters. Trainable parameters. Yeah, total parameters. Yeah, so it's this pruning has added one additional parameter per parameter. Okay. Let's get that going and start pruning from step 2000 when accuracy is greater than 98%. So if we reused these weights, then we could train it up as much as we like, and then when we're done with it, and we're like, hey, this is a good model, we like it, then we could bring it over to this kind of, we could make a new prune model with all of the weights that we have defined above, already pre-trained, and then we could, use this to just do the final touches. So this is going to have to train it and then trim it. Okay, so let's just review this code here. So we're compiling it again, cross entropy, atom, accuracy. Everything is the same there. Callbacks. We're going to do the update pruning step and the pruning summaries, which we weren't doing before. All of this, oh, it's interesting, they actually hard-coded in the number of epochs now. And before, it was 12. What? It's 12? That's weird. Okay, maybe my memory is not serving me correctly. Oh, we calculated, what? What are they doing here? Number of epochs, 12. What? But then they set it 10? I'm confused. Why would they do that? They're not doing this. Let's just do this right to the... I think they messed up. Let's change that. Batch size, epochs. Yeah, okay, this all looks good. Validation, so they're using test as validation. That just means that we can see it every time. And then they'll do the pruned model and evaluate it. Let's run it. Nice. Can we get this guy to show it? There's the second one. And where's the data? Scalars. Ooh, here we go. Oh, we got more data. All right, well, whatever. Let's take a look down here. Oh, sparsity is illegal. Using prune metrics. What? Okay. Well, I've never used it before, so I don't know if that's like a problem. I don't know. It's the issue with debugging stuff that you don't have experience with. I don't like warnings. Oh, it's info. It's just info. It's not even a warning. No problem. It's using something else. Okay, I'm going to assume that's all good. Whoops, went too far. Let's see how well it's doing. Where's the results? Here we go. Validation accuracy is 99.38%. 99.74% is the test accuracy. Sure. And there we go. Okay, 99.43%. Oh, it did really well. Yeah, that's pretty good for a single model and not using a group of models. Okay, let's save it. Continue training for 2 more epochs. Well, I already did it for 10. So this isn't going to work. That's why they had it for 10. I need to read ahead. There we go. Let's do 10. Let's just pretend that ran. Sure. Oh, okay, what's this doing now? This is checkpoint file, saved, save model. Note here to highlight. Restore model. We're gonna restore. Oh, okay, we're basically just making a copy of it here, fitting it, running it again. When saving the model, include out must be true. We need to preserve the data of the optimizer across sessions, right? When loading the prune model, you need the prune scope for deserialization. Prune scope. Oh, prune scope. That's a stripping the pruning wrapper from the pruned model before export for serving. Before exporting the served model, you'd need to call the strip pruning API to strip the pruning wrapper from the model, as it only needed for training. Strip pruning final model, pruned model. Okay. So you have to remember we totally skipped this. I'm going to say I skipped this. Okay, that's good. Let's just minimize that. Okay, so that's the stripped model, final model. Okay, cool. Pruned model. Let's save it. Compare the size of the pruned and unpruned. Let's take a look. Cool. Wow. It's much smaller. That's pretty cool. Okay, let's, that's pretty nice. Yeah, before compression, exactly the same size. After compression, quite a bit smaller. So that's really good for mobile. And in addition to that, it can really help us just zero out features that, like, not really a regularizer. Anyways, yeah, we could prune variables that we don't need. Okay, let's read this. Pruning a whole model. Prune magnitude function can also be applied to an entire model. Applied to all layers that are amenable to weight pruning. Layers, yeah, cause error. If your model has layers, the API doesn't know how to just apply the layer, yeah. Regarding prune configuration, the same settings, all printable layers. Okay, before we move forward with this example, let's address the common use case. We may already have serialized pre-trained and you'd like to apply weight pruning. we will take the original MNIST model trained, did it again. Trained previously to show how this works. In this case, you start by loading the model into memory. Oh, okay, nice. We wouldn't even have to save those weights before. You can then prune the model loaded and compile the prune model for training. Nice. Okay. So here we say we're going to prune it for four epochs, however you want to pronounce that. What country do you come from? And the end step is we're just going to calculate how many steps there are. Yeah, pretty easy. The begin step, we're going to start right away. End step, we're going to end right away. And we're going to just enforce 50% sparsity right from the beginning and end with 90%. Okay. And do some pruning every 100 steps. Okay, cool. So we could just wrap a whole model in these pruning parameters with a prune low magnitude, and that makes our whole new model. And then we could just immediately, where is it? We could just strip it after. That's nice. Okay, let's do that. Nope. Did not work. Okay, what's going on? Please initialize prune with supporting layer. Batch normalization. Maybe batch normalization isn't supported. It said v2, right? Please initialize prune, support layer. Should either be prunable layer instance or should support the prune registry. You passed. Batch norm. Okay. Just apply it in the per layer basis. You can't do it on the whole thing. So we're using TensorFlow 2.0 instead of 1.14. We're using the batch norm version 2. I don't even know if the batch norm, the old batch norm would work. That's interesting. So what is the model here? Model, loaded model. Which model is this saying? Let's find it. Where is it? Final model. Zip 1, yeah. Oh, this is bugging me. let's use this loaded model. And that's the original Keras one. Let's use this. There. Okay, cool. That worked. And it's double the size. Nice. Let's just print this summary twice. So this is before and this is after. Okay, cool. Well, there was a problem in their code. Maybe it was supposed to be model. I don't know. Okay, let's launch all this again. So now we're going to fit this for, I think this is 4, yeah. So we're going to take that saved model and we are going to just run pruning on it. Yeah, that's nice. We've saved it off. We get all these info messages again. So 99.18, it's pretty good. And this is almost done. Yep, wasting my life, scrolling up and down. Scrolling. Okay, it's done. 99.23, not bad. And let's refresh this, refresh. And graphs, scalars, and okay. Oh, so the training started at pretty high accuracy, and after we applied the pruning for four sessions, the accuracy dropped a bit. What's interesting is the test, the validation. The test went down a bit, went back up. It's pretty chunky. It's all right. Loss. The loss actually went down. Okay, interesting things. Interesting. I don't know why I want to comment too much on that. There's really not enough data to really draw too many conclusions. You know, I wouldn't go so far as to say like, oh, look, it decreased loss on the validation set, and you know, decrease the distance between the validation and test, and so maybe it acted like a regularizer. And no. Just like one training set, one test. I don't think we can draw any kind of conclusion like that. Export the pruned model for serving. Okay, well, this is the stuff that's cool, right? So here we stripped out all the pruning stuff. And we have a minimal model, and we can save it, and then it's ready to serve that off to TensorFlow Lite or somewhere else. That's cool. Okay, well that's all I wanted to cover. I'm just skipping through this. Post-training quantize the. Oh yeah, you could retrain it again. Quantize, conclusion. Okay. In this tutorial, we showed how you can create a sparse model with the TensorFlow Model Optimization Toolkit. You know, what I really liked about this is you can just wrap it. I really like that. Where did they do that? Right in here, right? They just took your model right? And this is just our basic model that we'd save, that no special thing was done to it, right? With our high parameter count, you remember all that, just our basic vanilla model. And we just wrap it in this code here in order to make it sparse and optimize it. We don't have to like put that in the model. And then in order to take off all of that, optimizing sugar, we then have, so then we run it, and then we have this just strip pruning. So, so let's try to put all of that code in one place. So here's what I want to do. I want, if I want to have some model, so my, so training model, so I want to take this guy here and take this guy and optimize him. That's what I want to do. So I want some function that say prune, and I put in some model, and I want it to prune it. And I'm not optimizing it, I'm pruning it. So let's build that function. Let's just go and yoink this code. Where is it all? Okay, just had to take a break there. So we were going to just copy that code. Let me just find it. Blah, blah, blah. It's not really, I'm not interested in that. Not interested, not interested, not interested. Not really all that interested. This guy here, I'm interested in. So that's something we'll want to do at the end. Okay. And then here, this all, we'll want to do something like that. And, let's just delete this. And let's delete that. Conclusion, fine. I mean, this was fun and all, but let's just get rid of it. And then here's where we defined it. Do we need anything before then? No, we just have the model that we're loading, and we're calling it the loaded model. Okay. And let's improve this. So I'm going to call it the loaded model. We want to take the loaded model and we want to make this function that given a model, we're going to train it for a bit. So let's make these parameters. Box equals 4. We're going to have to give it x train, y train probably. Yep. And this number of training samples is x train dot shape 0. And we have a batch size. I'm just going to make this batch size. Oops. What did I do? Batch size equals, I don't know, what did they have it at? 100, 200? Doesn't really matter. And epochs and print end step. Don't really need that to be printed. And then we have this new pruning parameters. I'm going to call it the pruning schedule. So all of this, I don't like it like this. Pruning schedule equals all of that, and then this is like that, and this is like that. Load model summary. Well, that's the model summary. And that's the model. And then we're going to give it summary. So this is the before and after, right? Just make sure we got everything okay. Frequency 100. Yep. So these we could make parameters too, but let's just get this going. All of this is just regular callbacks, log, pruning summaries. We need a log directory. We need to fix that up. I'm just going to skip it for now. Xtrain, yep, all of this, validation. Well, we don't have X and Y. You know what? Let's just get rid of this. We'll just use the global for now. Whatever. And then we have our score. And then our final model, which is actually result is equal to this. And then we could say return is equal to that. And then see, does that work? Line 11. What did I do at line 11? Don't need that. Okay, so final model is train, prune it, yep. And this is our loaded model. Okay, so we should be able to take our loaded model, and this in one go should do the whole thing. Take our model, and then prune it down. Cool. All right, so that's a nice little bit of code that we could clean up and move these parameters up to here, and this just prunes a model. Nice. Okay, so let's let that run, save it, and I'll put a link of this in the description. Maybe. I don't know if I'm feeling like sharing. All right, that's it. Wasn't really anything earth-shattering. We're just, pruning parameters to make our models smaller so we can run, on the web or on a mobile device, and showing that we can do that and still get pretty good accuracy. I mean, part of the reason why we can get still good accuracy is because our models are just like have so many free parameters. That's a lot of parameters. Here's the original model. That's just like a crazy number of parameters. Of course, we can prune a whole bunch. Yeah, that was kind of neat. If you stuck around Till now, I give you 2 free internet points. Nice. Awesome. See you next time.